then in between we have pi over 2 and 3 pi over 2. Okay, if we plug in any number between 0 and pi over 2, you would get positive. And it's negative, and it's positive. So the sine function increases from 0 to pi over 2, decreases from pi over 2 to 3 pi over 2, and increases from 3 pi over 2 to 2 pi. Let's repeat the process with the second derivative, which is negative sine. So this is cosine, which is f prime. So f double prime is negative sine of x. So let's graph negative sine. I know it's sort of cheating that we're using the graph to answer the question about the graph, but we just need to know when it's positive and negative. And this question is much more detailed. We're finding more intricate properties of the sine, like inflection points and max mins. So let's see, the sine curve would look something like this. If you flip it over the x-axis, negate the amplitude like that. Well, everybody should know that the zeros occur right there. So the critical numbers are 0, pi, 2 pi. And let's look at the number line for f double prime. So we have 0, pi, 2 pi. So if you plug in anything between 0 and pi, it'll be negative. Anything between pi and 2 pi is positive. So it's concave down, and then it's concave up. Alright, so let's look back more carefully at what we have. So increasing and then decreasing, that's a local max. Decreasing then increasing, local min. Here we have a point of inflection, I. Alright, so putting this all together, well, we know the graph of the sine, but now we understand it a little bit better, and we could figure out where it changes concavity. So let's draw the graph of the sine, making believe we sort of don't know it. So we increase until we get to pi over 2, then we decrease, then we increase. We're going to be concave down, and then concave up. So let's see. Now, the calculus that we did does not tell us that it's so symmetrical. We know that already from trigonometry. But what the calculus did tell us is that there's a point of inflection right here at pi. So this really is the point of inflection. We know we have a local max at pi over 2. So here's local max. And we know we have a local min at 3 pi over 2. Local min. And if we simply used the sine to get these few points and then connected the dots, see how we're concave up here, concave down here? Here we're concave up. We could get this graph, though we may not know exactly that it looks like this, but we can get a nice sketch of the graph just using what we've learned. All right, one more example. So there's a very famous graph called the bell curve. F of x equals e to the minus x squared. So let's compute the first derivative using the chain rule. And the second derivative using the product rule and the chain rule. So I use the product rule and then the chain rule and the chain rule in the product rule also. Alright, now we basically need to set these equal to 0 to find the critical numbers. First one is rather easy. So e to the minus x squared is always greater than 0. No zeros can ever come from the exponential. So the only zeros come from there. So negative 2x is 0, which implies x is 0. That's the only critical number, x equals 0. A little more complicated here. Factor and simplify. So f double prime of x is equal to e to the minus x squared, negative 2 plus 4x squared. Once again, no zero can ever come from the exponential. It just doesn't cross the x-axis. But this definitely does. So set that equal to 0. So 4x squared is equal to 2. Divide both sides by 4. X squared is equal to 1/2. So x is equal to plus or minus 1 over radical 2. Okay, so we have our number line for f prime. Remember, e to the minus x squared is always positive. So if x is negative, double negative will be positive. If x is positive, negative times a positive would be negative. So what we know is it increases and it decreases. So it's a local max. Number line for f double prime. So f double prime, we would have negative 1 over radical 2, positive 1 over radical 2. If you plug in a number like 0, negative 2 plus 0 times a positive is definitely negative. Plug in 100. Negative 2 plus 100 squared, huge number, positive times positive, positive. This is an even function. You get the same answer if you plug in negative 100. Positive, it squares to positive. Still positive, positive. Okay, so we're concave up, down, and up. And we have our points of inflection between them. Alright, so why don't you pause it for a minute and see if you can come up with the graph. So let's see. So it's an even function because f of negative a is equal to e to the negative a quantity squared, which is equal to e to the negative a squared, which is equal to f of a. That means it's symmetric about the y-axis. Alright, so let's see what the graph looks like. So we increase and then we decrease. We're going to be concave up and then we're going to be concave down. Let's see. Now, as a hint, it might be a little difficult to come up with the graph, but there are two things you might want to keep in mind. The limit as x approaches infinity of e to the minus x squared is equal to the limit as x approaches infinity of 1 over e to the x squared. As x grows large, x squared grows even larger. E to the x squared grows even larger than that. 1 over a huge number, this is a limit of type 1 over infinity, which goes to 0. It's a determined limit, which goes to 0. And since it's even, that means if you replace this by a minus infinity, you get the same answer. 1 over infinity goes to 0. So the graph has horizontal asymptotes at the x-axis. It's approaching the x-axis. So if you think about it for a little bit, the only option is something like this. What you get is the famous bell curve. It never crosses the x-axis, but it gets closer to it. This is the absolute max at the point 0, 1. It is a local max, but also a global max, an absolute max. See how we're increasing, then we're decreasing? We're fine. Concave up, and then we're concave down. We switch somewhere over here at 1 over radical 2 negative. And same thing, it's symmetric, so you have another point of inflection right here. So I and I. And that's it. That's how you graph using calculus. Without calculus, you'll never be able to figure out where the concavity changes. In fact, you won't even know what concavity is without calculus. So it's very useful. Now, why is it interesting to know concavity and points of inflection? Suppose you're investing in a stock. At the beginning, the stock is growing like crazy, then it levels off, and then it crashes down to minus infinity, right? Okay. When do you sell the stock? Well, obviously, you would buy low, right? And sell high. So you'd sell it right around here. But of course, you can never really do that. Nobody knows the graph beforehand. But if you can detect the inflection point, which is somewhere here, this is when the growth rate is slowing down. See, it's still increasing, but it's just not growing as fast. It's not accelerating anymore. Over here, you have positive acceleration, which means you're concave up. Over here, it's deceleration. You're still increasing, you're still moving forward, but at a slower rate. You sort of have the brakes on. But the problem with the brakes is eventually you'll start decreasing. It's just a precursor to the crash. So the idea is buy it when it's concave up and then sell it when it's concave down. Alright, so I hope you enjoyed concavity and points of inflection, and I'll see you all next time.